estimate the not GJR, we estimate the E-Garch, we estimate. Yeah. And then tell you how to do forecasting of volatility. And then we go to the multivariate Garch, which is called M-Garch. So I'll tell you a bit about mean, this is Garching mean, and then we go to M-Garch. M-Garch, we have to actually do the estimation. We can't do it in Python. That is something that somebody could, from you guys, may want to do that, or sort of implement that in Python and have your own package. It's missing for MGarch, multivariate Garch. So that will be the second part of this that I will tell you. I will give you the theory and then the implementation one time with one of them. Alright, then you have your own package and piece. Let's do E-Garch. And that will be an arch model. Then again comes Y. So let's look at that. So here we have a beta, we have a gamma, and then how many of these lags we have. Alright. Well, essentially you can have one beta, one of those, and then many of these asymmetric stuff. So that will be P, Q, O. So this is P, this is Q, how many lags there, and this is how many O's there. Asymmetric part. So we get E-Garch framework. Let's go there. Let's say P is 1, Q is 1, O is 1. Now one volatility will be E-Garch. And then distribution, we always let normal, right? So the default is normally distributed. So then we could use P or generalized error distribution, and so on. And let's do it. It's actually not a big deal. Simply change. Then we say print. And let's go into use E-Garch 111. E-Garch 111. So again, we have an alpha, we have a beta. Right? But remember, the betas are, this is log, logarithms. Right? These are log of volatilities. So when here, when we were there, then you were adding those coefficients, and then you were saying, okay, this is the persistence that we have here. So here is a little bit different, right? Because U's also don't show up in power 2. On average, they are 0. So the persistence is this, the coefficient that we have here. There's 0.94, but I mean, as we have had it before, so roughly it's the same. Gamma is negative, which makes sense. Well, gamma is indeed alpha. Sorry, I mean that, but you understand. So that's the asymmetric part. And that is negative. So that is negative. And that would mean that so the plus, minus becomes plus. So when shocks are negative, then the effect of past shocks grows. The law of volatility. Because logarithm is a continuously increasing function, so it means that if you have a negative shock, then volatility goes up. Yeah. So that is what we see here too.
We have alpha. What is beta? Beta is
The coefficient on log.
Yeah, the one that we. Okay.
This is beta. So beta is the same, but maybe I should have changed the. This is in line with the book, the parametrization. This is part Python is different. Yeah, you should be always like careful, but I don't know. Neither I had to stay with the book or with the Python, so I chose the book in terms of parameters. Right, so gamma is alpha here, and alpha is gamma under the curve. Right? And that is negative, most likely, because we have leverage effect. So we know it from the GJR. Okay. Good. Should we do a forecast? Volatility forecast. Let's do that. Forecast with the Garch 1-1. And with the E-Garch, then you need to take E to the power of equations. And then take expectations after taking exponentiation. So that's sort of what we have. Let's do with Garch 1-1. Do a one step ahead forecast, okay? But these are also in detail on the slide, a little bit ahead. You see them? But let's see in terms of implementation. The one is step ahead forecast. They are very simple. So that's a Garch workload. And if I want to forecast, let's say I have T observations. Returns, and we have T equal 1 to T, and then we do estimate. So we want the forecast of T plus 1 given the information of T squared. So that is what we need as a forecast. So if I want to calculate this, let me write sigma T plus 1 squared. It will be alpha 0 plus alpha 1. UT, so that will be UT squared plus beta 1 sigma T squared. So that's sort of the recipe that I have. If I go what is the red, then it becomes this. If I want the forecast, the first I need to estimate those parameters. Right? And you know the forecast are indeed expected values. And it's an average. So but when I'm at period T, then the residuals are known to me. Because I know mu, I have the return in period T, capital T. So I can estimate or get the residual at period capital T. That is not a big deal. Right? So that would mean that this will become alpha 0 hat plus alpha 1 hat ut hat squared plus volatility hat squared. All of these we know. Everything is known to us. Correct? So then we have the residual, we have the last volatility, we have all of those coefficients. Right? We have all of those coefficients. And then we plug them in, and then we have a one step ahead forecast. So if I want 2 step ahead, so one more. And what do? I don't have the residual. And I don't have sigma T plus 1. So but what I can do is have a toothpaste. Then what do we do? I mean, sigma T plus 1 we don't have, but we have a forecast there.
Yeah.
So we can plug in.
What about like sigma T squared? We can't have that, but we don't have to have. We don't need to have that.
We have it. We have the hat. I
So
plotted
it
the
depends on the hat
true return, so the difference will be T. That is what we know.
So I thought like we don't need that hash anymore because we know that.
Okay, but that's an estimation, we don't have the residual. We don't have the true parameter, the true residual, we have an estimation of the lead, we don't know it, right? We have an estimate thereof. Because we have an estimate, then you will be your half. Right? Clear?
What about the sigma?
Half, exactly.
Did the same because we don't.
Well, we don't have the we do not have the true volatility, but we have the estimation thereof. This is what we plot. Right? Good? Good. Let's go there. So if I want a forecast of T plus 1, T plus 2, given the information of T squared, then well, maybe let's just do the volatility. Right, so because I just want volatility. So here, take that off. Then we get square root of. Right. Well, alpha 0 will half, alpha 1 will half. This we don't know. The residual in period T plus 1. Right. So we can plot an average of. What is the average? It's a station. Well, that's the best thing we can do. Am I right? Here we go.
Yeah.
Let's say you can take this to the power of 2. Right? And take an expected value. Right?
So we did the GT, the IID on the 0, 1.
So let's write it here. An expected value of 3t plus 1 squared is equal to expected value of sigma t squared, sigma t plus 1 squared. Right, so that is what we have. And expected value of sigma t plus 1, I'm sorry, we have to be careful here. That is expected value of alpha 0 plus alpha 1 ut squared. Alright, that's an expected value. Plus beta 1 sigma t squared. Alright, so I need an expected value for all of those. Right?
Yeah.
So, I mean, that's sort of conditional, that's conditional on the past, it's always conditional expected value. So now, average of this will be the same as average of that. So this guy or the expected value is the same as this. So then I can plug in the expected values that I have for them. This is the same as this in expected value. And this I can plug in here for this sort of, I don't have, alright. So that will be expected value of sigma t plus 1 squared, but that's the same as this, which is this. So these two in expected value are the same. Right? Then I can plug in basically the values for them. Then we plus beta 1 half. Alright. Now becomes the volatility in period t plus 1, which is this. And we plug it. It was too fast. Huh? And maybe you're.
I'm just thinking, yeah, I understand the very nice. Just thinking. Do we need to like, can we do the stationary again to find the mean of U?
Oh, we can. We can basically do that and then plug in, we have alpha 1 and so on and so forth. We can
Get rid of the time.
But that doesn't make any sense. Because they will be the same.
Okay.
Right? On it. Well, that makes actually no sense, not because they are the same, but because of some other reason. I don't know. Like what we see here. that we have at time t. Right? So everything, whenever we do that, then we always condition on the past. And when we were doing the expected value of, say, t squared, then I was not conditioning. So which was essentially alpha 0, what it is, alpha 0 minus this for Lagrange 1 first. Because that's the persistence, so 1 minus the persistence. What alpha 0 is alpha. This is unconditional variance. It's unconditional. What we do here is condition. We condition on what we have, what we know. That's different from the unconditional. These are unconditional. Mitosis that you asked, this one is the derivation, sort of for virtually really life. Then this is also unconditional. But these are conditional. All of them are conditional. Because we condition on the past information. So the forecasts need not be unconditional expectations. Right? So because that will be a simple mean, a simple parameter that will not actually change at all. Because on average, then you have a mean. Right? And that will be the same for all of the values that you got. But this is what the nice thing about that is that it is conditional, so it takes into account what has happened recently and updates essentially the estimates. Right? All right. So then here I was saying that these two are this is the same as that in forecasting. So this to the power of 2 will be this simply, no big deal. And then we can go on and on. Right? So with 2 periods ahead, then we have this to the power of 1. With 3 periods ahead, will be this to the power of 2. Right? So the effect actually reduces. Right? Like we were doing in forecasting for AR models. That's exactly the same. So let me also show you. Oh, they are here. I did actually the derivation already on the slides. Alright. So here are the equations. 1 is 7, 2 is 7, 3 is 7. And then they depend on the past values. Alright. And let's see how do we calculate the 1 is 7. Will be expected value of this given the past, which is what we know, that is what we have. We know u, we know sigma, we plug in, we have 1 step. Alright? That's exactly what I got. And so if I have 2 step ahead, right, then that will be this forecast 2 step ahead given information up to period t, will be expected value given the information set up to period t. Alpha 0, then this guy, plus the other one. Alright. So this one is known. That's a 1 step ahead forecast. Alright. Because that is the expected value of u to the power of 2 is the same as the expected value of sigma to the power of 2. And that's 1 step ahead forecast. This is by itself a 1 step ahead forecast. Then you plug in alpha 1 plus beta, will show up. So that will be sigma t plus 1 given the information in period t. Alright? And then we can clear?
It's also u, right? U squared.
Right. On average, this will be sigma squared. Right. And then we don't have sigma squared in t plus 1, but we have a estimation, forecast there. We plug in for that. That is also something that we have with beta 1 half. I'm not sure. So that is 1 step. 2 step. So 1 step times the persistence plus the constant gives you 2 step. It takes you 1 step in time. And in general, so if you want to have more, right, then you can play around with this equation and then add the more, then geometric sum will show up, and then you will be good to go. Alright. And then alpha 0 times that will show up. And then alpha 0 times this to the power of 2 will show up for the next step, and so on and so forth. Then you will have alpha 0 plus alpha 1 plus beta 1 to the power of 1 plus alpha 1 plus beta 1 to the power of 2, and so on and so forth. Right. And then the first one to the power of s minus 1 or t minus 1 also shows up. Alright? It's happening in the first one, then s is 1, then this term goes off. Right? So, and so on and so forth. So that is what we have here. Right? If s is 2, then you have here 2 minus 1, and this shows up. Alright? And we can continue onwards. Is it clear? Yes. Maybe you should do maybe you should do an exercise with it. So, well, we can do one exercise. So let's do forecasting here. Let's do it that way. Once we implement that, it will be clear. Alright? So we need the parameters from the Garch 1.1. So this is Garch 1.1. Let's look at the print summary. And there is an omega, which is alpha 0. There is an alpha 1 and beta 1. So these are the parameters that we need. Alright? And let's obtain parameters. So using Garch 1.1. Let's obtain the parameters. Good. Parameters of what? We have an alpha 0. Alright. And alpha 0 is, well, let's look at Garch itself. The wrapper is pretty much the same across all of the models. So that's the Garch. And there is a params. You see? So let's see what is in params. Garch 1.1 dot params. And these are all of the parameters that we have. So we can get the alpha 0. And alpha 0 is Garch 1.1. Let's see if it works like that. It should. So that is not subscriptable. We say we need an alpha. Oh, we should say params. First params. Then it should work. So that is the first. What is it explaining? So that's alpha 0 and that's the coefficient. Good. Let's get alpha 1. Alright. And alpha 1 is the second inverse. Then we need beta 1 and that will be the next. Alright, so that's beta 1. So I have alpha 1, I have beta 1. So I have all of these parameters. Right. Now, well, I also need the residual, right? Or at least the last residual I need. I need the last volatility. Right. So, well, sigma at period t is Garch 1.1 dot conditional volatility, the last. So then I have sigma. That's sigma t. And in the very end, then I need u at period t, which is Garch 1.1 dot residue at period minus 1. And then will be the last residual. Alright? The last residual is pretty big. Right, so we are variable below them. Alright, so now if I want to produce a forecast, so one is step ahead, then I have a recipe. Alright, so, one step ahead forecast. So that will be a script and np.sqrt of alpha 0 plus alpha 1 times ut squared, squared like so, plus beta 1 times 60 to the power. That's a one step ahead forecast for the variance. Is it now better? Maybe. That's one step. So if I want a two step ahead, well, let's maybe take this and call it sig 1 t is this, and that is sig one step ahead using t observation. So that is how it is. Now let's do two steps ahead. So that will be C2 using the information of the QAT, and that will be NP SQRT of, well, let's see, so we have an alpha 0, right, plus alpha 1 plus beta 1 times 1 step ahead to the power. So it drops. Well, we can hold it. So. Right? And if I want two step ahead, then what do I do? Right, then we can basically use this recipe, right? To say S is 2, this is value for S is 2. With the alpha 0, alpha 1 plus beta 1, S is 2, so 2 minus 1 is 1, so that will be to the power of 0. And then here we have 2 minus 1 becomes 1, so this times this. Alright. But that was two step ahead, that is what it is. So 6, if I want 6, 3, right? But let me just plug in S equal to here.
We missed some hardware.
Well, let's check. I think no. Right? Sorry, why it works? No, it's correct. No, it's let's write it out, so let me make sure. Alright. So, sigma 2 is the back to the power 2. That is equal to alpha 0 summation, I runs from 1 to minus 1. 1 plus beta 1 to the power of I minus 1 plus alpha 1 plus beta 1 into hats and times, well, to the power of S minus 2, so S minus 1 times sigma 1 squared. Good, so that's a summation from 1 to 1. I is then just 1. 1 minus 1 is 0, so alpha 0 plus. So 2 minus 1 is 1. And we have alpha 1 half plus beta 1 half times 1 stability. Well, as we have for a while. So that's sort of the same formula. You can put it in a loop and then calculate whatever for volatility. I should give you time so you can set this. So now that we are here, then let's do something more. But let's say alpha 1 plus beta 1 is smaller than 1, and of course it's smaller. So can you calculate the limit as S goes to infinity of sigma squared of S given T? So what will be the long run? Very far ahead for it. Not 2 step, not 3 step, or infinite. Right, so alpha plus beta 1.
Oh, no, sorry.
1, 0.
Plus,
Wait.
so geometric.
Sure. Very nice. So first this goes off
Yeah, the other remain.
because alpha plus beta is smaller than 1. S will be very large, so that shrinks to 0. So
But
that
the
goes,
other,
and that remains. That will be alpha 0. So summation, I runs from 1 to infinity, alpha 1 plus beta 1 to the power of I minus 1. Good. That's the geometric sum. That's 1 set. Then it's done summation, I from 0 to infinity, alpha 1 plus beta 1 to the power of I. So instead of counting from 1, then I count from 0. There is an alpha 0. So that will be alpha 0 divided by 1 minus. And this is unconditional variance. So that's unconditional. In the long run, then you hit the unconditional variance, which makes sense. So in the long run, then sort of the small variations wipe off, they disappear, they vanish. And only the average, which is the longer variance, the unconditional variance is there. This you know, right? The geometric summation. Right, so that's how you do forecasting with a gauge, which is nice. But that actually works just 1 step, 2 steps ahead. So you can actually without get too far ahead of time. Alright, you know that. The forecasts, or one says that we are all dead in the long run. So are the forecasts. They're not done. Very good. So if you want to do forecasting with eGarch, let's see how eGarch works. But then I see you are going to calculus. So there is more. Calculus stuff for you. take things, and if I exponentiate both sides, then I get this equation. Then, so if I'm at period t plus 1 given t, then I simply have this. And simply plugging one of the values. That's an exponential, so that's not big deal. Then you have one step. Alright? 2 step ahead will require calculus. Right? So because in this case we use. Alright? And then we had this, all of them meeting out. Alright, so if I want to do a little further, so 2 step ahead. Sigma t plus 2 squared. And I now here e to the power of omega, e to the power of beta, t plus 1 squared, gamma t plus 1, sigma t plus 1, right? E to the power of alpha, ut plus 1, sigma t, minus square root of. If I want this, then I have to take an expected value. So expected value of both sides. Okay. So, and then once I have an expected
Absolute. Or the UT.
so you need that. Okay.
T plus 1.
Yeah, very nice. Maybe.
Yeah.
That's okay. And so now we have to take an expected value of this guy, right? Let's see, there is one more.
Not one.
Oh,
Just
so it's not necessary.
Very good. Just one. And then here too, right? Because I just have it here and then. So here we have e to the power of gamma and normal. Right? And this is also normal. We can actually put them together. Right? These two normals. Right? Well, we don't have actually any problem with that. Because that's a one step ahead for us. Right? So if I want one step ahead for us and I plug in here, then I need the expected value of this. Right? And then it is e to the power of gamma. So because this is normalized, then here we have, say, some z, and z is a standard normal. Right? Plus, say, alpha, absolute value of z minus, well, square root of 2 pi. So we need this expected value. We need to calculate an expected value of this square. That's not z here, or absolute value, or rather, e to the power of something.
We can call that B, but because we have at least B2 or BT plus 1. Or,
You mean this?
yeah. So not exactly B2 plus 1 or there.
Let's call it B. Alright, and that is a standard norm. Right. Right. This you should be able to calculate. Alright. And because, well, that will be e to the power of gamma v plus alpha absolute value v. And that's a constant, maybe the constant I can take out. That will be e to the power minus alpha square root of 2 pi. And then the density is 1 over square root 2 pi, e to the power of minus v squared half. And that's an exponentiation. This is also an exponentiation. And that is something which is known actually with B. just for the fun of it. I don't ask hard questions or lengthy questions on the exam, but it will make sense to calculate that. So, but if you want to do forecasting with an EGAR, we need a little bit of, and once you do it, then you have it forever.
So can we use like the theorem like exponential often normal because we can it's a linear combinations of normal.
That's right. But that's an absolute.
Because it might not be. Yeah, it's not.
So you should break it into two pieces, from minus infinity to plus infinity.
Oh.
Indeed, what you can do, I mean, just to see what is possible to be done here. Let me open it a little bit. This is like integration from 0 to infinity. When it is positive, then it is positive. We have e to the power of, well, let's call it theta 1. V minus 1/2 v squared. And that is what we have here. 1 over square root 2 pi. And it is theta 1 power. That's alpha plus gamma. That's very easy, you can complete the squares. Right, so you can complete the square right here. Then you have a quadratic function, and then we go. And then the other one is also the same. So here we have 1 over square root of 2 pi integration from minus infinity to 0. Now it is negative. And here we're going to have e to the power of gamma minus 1. Minus 1/2 v squared. Do you understand what I meant? What did I say? Well, complete the square. Right. So you complete the square. Let's see. So minus 1/2 I can take out of this will be v squared minus 2 alpha plus gamma. Then if I want this to be quadratic, what is missing is to the power of what? That is this times the other one, right, minus 2. And here I need plus alpha plus gamma to the power of 2 minus alpha plus gamma to the power of 2. Right, that's the numerator, the power. The power is this. Now let's look at that. So these two we can put together. So then we read minus 1/2 of v squared as v minus alpha plus gamma to the power of 2. Minus minus becomes a plus. Right? This integration is then we have 1 over square root of 2 pi, integration from 0 to infinity, e to the power of minus 1/2, v minus alpha plus gamma to the power of 2, dv. And that's simple coefficient, so you can cut out as an multiplication. That's e to the power of 1 alpha plus gamma. So that's a Gaussian. And so that's e to the power of 1 minus 1/2 v minus some mean. And then the variance is 1. So that's the density of the normally distributed random variable. The variance 1 and this mean. Right? So that's something that you know how to deal with. Right? And then the same thing you do with the other one, and then you will have some expression. So if you want, then you can complete it, because you showed interest and I wrote a little further. But that's not what I want. this, then we need the expected value, and once we have it, then we can go on. If I give you a question like this on the exam sheet, then I will give you the expected value expression, such that you plug in, which is sort of not already in the calculus. This is not a calculus class. Calculus is important. All right, so we have half an hour, and I want to talk about the next topic. All right. Well, indeed, if alpha was 0, if this was 0, then y becomes 0. So that then you really need to separate the two pieces. It would have been 1, and things would have been easier. Yeah. Well, you understand that when V is normal, then gamma times V is also normal. So e to the power of the normal becomes a log normal distribution. Log normal distribution has well-known mean and variance. Here we need the mean and the variance, and that is part two. That was the end of the univariate. Everything we were doing was, as I said, one variable. Alright? Just one market. Alright? But we also have multivariate large models. Multivariate large models, let me just motivate you sort of to say that why are they useful. I didn't tell you why volatility is important and why to be estimated, because I know you know that volatility is interesting. And knowing it and being able to forecast it is good. So that's sort of useful in finance. But for one period, then I need a bit of work so that I can tell you why, for example, in a unit. For example, if you have an asset I, and I go to CAPEX, market minus the risk-free rate plus the using value every time for asset I and price. And this we estimate using Euler's, say. So what do? We have? We can also use other things. We learn how to estimate that. The Rorty window, we have for non-parametrics, localized in time. But then we can estimate it on the zero orders. What is the formula x prime x minus 1 x prime 1, as you told me on 1. Right? And then that was like the covariance of this point is y and x. Right? So that will be the covariance of yt and xt, right? Divided by the variance of x. Right? So that is how Kaplan is estimated. So if I want the variance of xt, I can estimate. I know how to estimate. Right? So that's an asset return, and it should be just discussed. Right? When using large models, then we can estimate the volatility of this in a time varying frame. or you ignore the time variation, and then just use all of the sample, and then get a simpler variance using the sample. That's something that we can basically get. Let's call it heterogeneity of x at period t. So that is what we need. But this covariance we can also estimate in a time varying framework. So what we need, so if I want the covariance, then well, let's look at the covariance matrix of y and x. Then there will be sigma x t squared. So we put it in a matrix. Then let's say here we have sigma of y at period t squared. Alright, so that will be the volatility or the variance of y at period t. Alright. Then we also have the covariance. Alright, so let's say sigma of x and y and period t. Then sigma x and y period t. And that's a covariance matrix, right? So let's call it sigma t. Right? That's a covariance matrix at period. Right? So as I said, so in univariate large models processes, then we were actually focusing on only one variable. Right? But if I'm actually going to focus on two variables, then my variance becomes a matrix. It becomes a 2 by 2. Right? So instead of, so what was Garch? Garch was saying sigma squared equals alpha 0 plus alpha 1. Ut minus 1 squared plus beta 1 sigma t minus 1 squared. Well, that's a simple linear equation that we have, recursive equation. So what we can do is that we can take this off, this sigma, and then replace it by a covariance, by a matrix. And then you start doing the estimation in the matrix form, right? So in the matrix 1. And that becomes a multivariate Garch model, right? Or M-Garch. Right? So multivariate Garch models or M-Garch. So if I do that, then I can have the covariance, and I can have the univariate ones, and I can plug them here. Right? So I plug in the numerator, I plug in the denominator, and this covariance matrix is time varying. So covariances are time varying, and the variance is time varying. So beta, and beta will be time varying. Right? So that's sort of one of the applications that this has. Right? On the other hand, the other application that this has is that, well, so for a small set of assets, right? Well, you know that whenever you want to do a portfolio, you want to put a portfolio together. What are the inputs? One of the inputs is the mean of the asset. We need the mean of the asset returns, right? Such that they go into the MPT. And another input is the covariance matrix. Right? So you need the covariances, because the covariances actually are an input to the portfolio theory. But I meant the variance of x, right? Or, well, it doesn't matter, right? Excuse me, though, but you're right. So the covariance matrix also has another interesting usage. There is another mistake. Right, so the covariance matrix has another interesting usage. Apart from that is the input that you can give to MPT. But if the asset numbers are very few, right? So time varying assets, time varying correlations, and then so they go in, then they're making a scheme maybe affect that you have for your portfolio. Right? That will be a little bit hard to do, but still that's another usage. And another usage of this is hedging. Right? So hedging is a mechanism that you use to sort of do risk management. Right? And then how much or optimal hedge ratio is something which depends on the covariance matrix. So how much should we hedge? Alright? I mean, the optimal hedging ratio could be also time varying, and that is, well, that could be also, these models could be used to give us the optimal hedge ratio. I will do these basic applications as time passes. First, we need to know what these models are, how to estimate them, and then we will do some application. So estimating from capital, sort of using, starting from capital. So now, with this, then we know how to estimate the capital meter in four ways. The first three we know, OLS, running with OLS, non-parametrics, and that's number 4. Alright. Now let's see what these models are. They are challenging models. Alright. Let's just start with the first model. The first model is called VEC-H model. VEC stands for vectorized, or vectorized actually version of the matrix. And H stands for the heteroscedasticity. Before I go on, Uwe didn't do multivariate Gardner. No. So that's totally new. Right. The previous one was no. Okay. So let's see. Here, if I have a bivariate model, then let's say that we have the heteroscedasticity looking like so. So then you have H11, 1, 2, 1, 2, so that's symmetric, and 2, 2. Correct? So here there are 3 processes, 3 basically elements that we have to model. That is H11, H12, and H12 and H22. So there are 3. So we don't need to look at all for other processes. Now, the error terms that we have also, well, previously was 1-dimensional. Now it becomes 2, because there are 2 assets and there are 2 errors. That is what we have here. Now, this is Tim, Bolesiev, and Engel and Woodbridge. That's our own Woodbridge. This is Robert Engel. Then they basically proposed 90A to do the following. Right? To say, okay, let's vectorize this function. All right? So this sort of matrix and make it a vector. In this vector, then you have this, and that. These 3. So that becomes a vector of size 3. So 3 rows, 1 column. And it is equal to vectorized version of all of those. So here we have U times U prime, which becomes U1 times U1, U1 times U2, and U2 times U2. So there will be also 3 elements. They are here. Right. And then here we have the vectorized version of H 1 period back. Right. So this is like sigma squared, UT squared, sigma squared T minus 1. The same structure in Garge, but in a matrix or sort of vectorized form. Now we have these matrices, sort of these coefficients. Before we have the alpha 0, alpha 1, beta 1. So now it becomes C, A, and B. And these are matrices. Okay? So they're matrices of size 3 by 3. Okay? So there are 3 elements in here. That's a vector of 3 by 1. And that's a matrix of 3 by 3. So here we have 9 elements, 9 parameters to estimate. Another 9 becomes 18. Plus 3 becomes 20. So though we have 2 assets, the number of parameters that we estimate in VEC H models is 21. Right? There are 21 parameters to be estimated. And that means that we need a lot of observations, which is not a problem when we have financial data. Well, good. So that's sort of what we have as a first model. Let's say simple generalization, and that is the VEC H model. Now let me give you some stories. Right? I mean, first of all, because the number of parameters are too many, so 9, 9, and 3, then some researchers said, okay, let's do sort of some reduction of these parameters that we have. Right? They started by saying that let this A and B be matrices but diagonal matrices. That means that all of the off diagonals are zero. So that becomes a diagonal vector H. So the diagonal vectorized heteroscedasticity model. So the diagonal vector H is simply that A and B become diagonal. So that is sort of, they are sparse matrices. There are not too many parameters to consider, but there are a lot of zeros in there. But now, I mean, there is a problem with the vec H and its diagonalized version. Because here we are not estimating a dynamic matrix equation. Rather, we vectorize it, so we sort of, the structure of the matrix, we make it go. It doesn't exist anymore. Because we vectorize, and then we sort of glue them together, put them back in a matrix. Right? But this is a matrix which is supposed to be a variance covariance matrix. And the variance covariance matrix should be positive different. Right? Now, one of the problems of vec H and its diagonalized version is that there is no guarantee whatsoever that it delivers a positive definite matrix. But that's a starting point. Right? That was one of the earliest models that came out when one wanted actually to look at the diagonal, the multivariate basically large models. Right? We will estimate and sort of implement them. Well, there came another then model a bit later. So that is BEKK. That's Baba, Engel, and two other K people. Sorry? Engel, Kroner, and another one. Right? So B is another person. It's BABA. I don't know why the names are not there. I don't know the story behind it. But that's the BEKK one. I call it Baba because that's easy. But then with this actually, the idea is very nice. I mean, they said, okay, maybe it's if this guy is supposed to be positive definite, then let's start with the summation of positive definite components. Right? Instead of using a vector A as the constant, then let's have W prime times W. Right? So that becomes, well, that's a quadratic function by itself, so that becomes positive definite. And then here is also a quadratic form. Alright? This is also a quadratic form. Alright? So that becomes positive, so all of them. But now the problem is that, so it is simple, handling this equation and sort of working with this could be a little bit hard. Right? Because, well, it is like a sandwich, and this is the butter, which is interesting for us. It's hidden between the breads, so it's sort of not so easy to extract it when it comes to sort of doing some recursiveness solutions. If you want a solution of this, then you should do it recursively like we do with the AR model. And it's a little bit tricky to handle, but it sort of resolves the problem of vec H that was not guaranteeing us to bring a positive definite in the model. So it's a little bit hard. So another basically model that we have is by Borislev, and that is sort of simple. So it came in 90 earlier. And then this guy actually said, well, let's take things simple. All right? Let's say, okay, what is the covariance? Covariance is the correlation divided by the standard deviation. That is what the covariance is. Correlation is the covariance divided by the standard deviation. So the correlation becomes the covariance times the standard deviation. Right? That is what we have. So if I multiply the correlation with the standard deviations, then I get the covariance. Right? The idea here was that let the correlation not to be time varying. So that becomes a constant correlation model. Right? That simplifies matters. Right? That's a constant correlation. Correlation is constant, but the covariances change. Those covariances are the correlations times the standard deviation. The standard deviations are functions of time. They go up and down, but this is a restriction. So we restrict the correlation coefficient to be non-time variant, time invariant. And then, but in any case, then we get a time variant covariance. So if it is like so, then well, there is a time zone. Well, this should be II, not IJ. Please correct that. If you can. Yeah. So this is the idea is actually very simple. Because, well, this is HII. That's the covariance of acid I. Right? I say 1 and 2. Then it is actually a very simple gauge. It's a gauge as it was. Thus the sigma equals a constant, the path shock to the power of 2, the volatility 1 period back. Right? So you have 1 acid, 2 acids, or say n acids, so that's II. Then Hij will be simply coming out of this. So here you model that, you model take your square root times some parameter which is the constant correlation between acid I and J returns, and then you get the covariance. Right? And it's also multivariate. But so to speak, you estimate the correlation, the standard deviations one by one, and glue them together. Right? So glue them using a constant correlation, which is 2, 3%, and so on and so forth, right? Or 10%. Some number between 0 and 1. Which we can estimate, of course. Right? So that becomes the constant correlation model, or the CCM. It's also called CCM, constant correlation. So that was interesting, surprising, beautiful, simple, and so on and so forth. But then in practice, it was not actually matching sort of the behavior of the data because the correlation being constant is a strong assumption. All right. So that sort of was not so interesting. And then time passed, and Engel in 2002 came up with a dynamic correlation, conditional correlation model, which is called DCC. Right? So the other was constant correlation model, this is dynamic. Correct? And then what he did was, again, he started with a simple Garch specification. But then he said, let the correlation be dynamic. Alright? So he made up a correlation matrix, which is a dynamic model. Look, this is Q, alright, some Q, which depends on the past shocks and the past values of Q. Alright? So then calculated the correlation of this. Alright? So I mean, in what sense? You have 5 minutes. For example, let's say you have a covariance matrix. Say 3, 1, 2, and 4. Alright, that's positive. Alright. So let's take the diagonal elements of this matrix and what it would be. So let's say Q. And then let's say define Q star. Q star will be, well, that is what we have. That's the element wise, the square root of QT. Alright, so that's sort of what we have. Alright. Let's say here we have a square root of 3. Alright. Square root of 2, square root of 1 is 1, and this is 2. Alright. Well, let's look at the diagonal of this. then this will be 0, and this is also 0. Right? So that's the diagonal, this dia that we have here is indeed takes Q, so matrix, looks at the square root of it, and then takes the diagonal element. And then let's invert this. So if I want to invert that, because that's diagonal, then it would be 1 over square root 3, 0, 0, and 1 half. Alright, so that's sort of what we do. Good. Now, well, let's print and post multiply this with Q. Alright. So here I have this diagonal of Q star minus 1 times Q times the diagonal of Q star minus 1. Let's see what happens. Let's see what is going on. So here we have 3, 1, 2, and 4. Alright. But actually you should understand this because when we do the implementation, it will be a little complicated. Right? That's sort of why I do this very simple exercise. And then let's post multiply by this. That will be 1 over square root 3, 0, 0, 1 half. And then here 2. Then we will 1 over 3, square root 0, 0, and 1. Can you please do the multiplication for me and give me the matrix in this last 5 minutes? Just go. Who is faster? We'll get a capital. You have it.
I have 1 on the 1 over square root 3, 1 over 2.
So here you get 1, here you get 1,
Yeah.
here,
1 over 2 times square root 3.
alright, and here.
1 over square root 3.
Alright, very good, thank you very much. So when this transformation, which is called R, indeed makes the diagonals 1, normalizes them to 1. So that's indeed a covariance matrix. So use a covariance matrix. And this guy normalizes in such a way the diagonals become 1. This should also be 2 square root. Well, this is not a covariance matrix. This is some matrix. Right? Then you will have basically these alpha diagonals to be some numbers which are normalized by the square root of the diagonal element. Right, I mean if I had this 2, right, then, well, so it's a covariance matrix, it's symmetric. Then here you will have had also 1 over a square root of 3, I guess. Right. Then we need 2 divided by 2 by square root of 3. Yes. So if I had covariance matrix, then this transformation we make it in such a way that the off diagonals are correlations. Yeah. Correlations. So this is a correlation matrix. R is a correlation. Simply because we normalize QT with the square root of the diagonal elements. Right? And so when QT is estimated dynamically, then so is the correlation matrix estimated dynamically. Right? That's how the dynamic sort of the status in the correlation matrix is in the small. Right? So this is why it's called dynamic correlation. So I told you 3 modes. Vec H, the constant correlation, and the dynamic correlation. Tomorrow I will estimate that. Thank you very much for being there, for catching my mistakes, and listening carefully. Tomorrow we'll do some application.
I think that is not symmetry. We use another calculations and it's not symmetry. That is 1 over 2